In the world of aging research, most breakthroughs tiptoe in politely, blood tests, lifestyle questionnaires, carefully followed clinical trial protocols. But sometimes, science learns the most from chaos. That's exactly what happened when researchers turned their microscopes toward the brains of people who had died from sudden accidents, victims of trauma, not time. What they found wasn't just a snapshot of damage, but a remarkably clear mirror of how the brain ages, at the molecular level, long before the signs show up on scans or in symptoms. These were not elderly patients or those in neurodegeneration studies. They were often younger adults whose brains revealed a silent storm already brewing. What made the study so unusual was its reliance on real-world tragedy to unmask slow-motion biology. Instead of studying elderly volunteers or people with dementia, researchers analyzed post-mortem brain tissue from otherwise healthy individuals who died in unexpected ways: car accidents, falls, blunt force injuries. Because their brains were preserved rapidly and weren't altered by long-term disease, the tissue provided a rare, unfiltered look at the unedited aging process. Think of it as a freeze frame of the aging brain before life and medicine had a chance to interfere. What emerged was startling. Even in people as young as their 30s or 40s, patterns of aging-related decline were already detectable at the cellular level. Specific regions, like the prefrontal cortex and hippocampus, showed early signs of synaptic loss, increased oxidative stress, and shifts in gene expression linked to inflammation and energy metabolism. The changes weren't catastrophic, but they were consistent, suggesting that aging isn't a cliff we fall off later in life, but a slow unweaving that begins far earlier than most of us think. One of the key findings involved glial cells, the brain's unsung maintenance crew. In trauma cases, these cells are known to activate rapidly to contain damage. But even outside of direct injury zones, many of the glial populations showed a subtle, creeping shift toward the same activated, inflammatory profile seen in aging and neurodegenerative disease. It's as if the biological wiring was already primed for defense and dysfunction, long before age or illness demanded it. This suggests that the brain may walk a thin line between resilience and fragility for decades, until a trigger like stress, poor health, or yes, even trauma, tips the balance. Another striking insight came from mitochondrial changes. In many samples, mitochondria, the power plants of the cell, showed early-stage dysfunction that mirrored what's seen in older adults. They were still generating energy, but with signs of oxidative overload and diminished efficiency. This kind of dysfunction has been implicated not only in aging, but in conditions like Alzheimer's and Parkinson's, suggesting that the seeds of decline are often planted early, smoldering quietly for years. What's quietly revolutionary about this study is its message: the body keeps the score, even when life is cut short. These donors, whose deaths were sudden and tragic, offered something rare to science: a chance to see the brain in its midlife form, caught in the act of early aging. Unlike traditional aging studies, which often focus on the end of life, this research highlights the fact that aging is not a process that begins in retirement. It's something we're constantly undergoing, invisibly, while we're still young enough to think we're invincible. It also reframes trauma not just as an acute event, but as a lens. When the body is exposed to sudden physical stress, it reveals its weakest points. In that stress response, like a building under a controlled demolition, scientists can observe which parts crack first. It turns out, many of the same brain structures and molecular systems that respond to trauma are also the first to buckle under aging. That overlap may help explain why traumatic brain injury increases the risk of later-life cognitive decline, and why early life adversity, both physical and emotional, can accelerate biological aging across the entire body. So while these findings are rooted in tragedy, they illuminate a hopeful path: early detection. If researchers can identify which cellular shifts mark the start of brain aging, they can design interventions, nutritional, pharmacological, behavioral, that reinforce resilience before symptoms emerge. The trauma wasn't the cause of aging, it was the flashlight that revealed where aging had already begun. In a strange and sobering twist, those who died suddenly may end up saving many more lives than they lost. Their brains told a story most of us will never see written in our own until it's too late. But now, thanks to their unintentional contribution, we know where to look. And maybe, just maybe, we can slow the story down.